Huang Lab, the team behind BlockEmulator, is a blockchain research group at the School of Software Engineering, Sun Yat-sen University, led by Professor Huang. The lab has over 20 active members, from researchers and PhD students to master's students and visiting scholars. Together, they have produced the BlockEmulator platform and a long line of peer-reviewed papers in top venues. Now, let's dive into BlockEmulator itself. In this tutorial, I'll introduce BlockEmulator, an open-source platform for experimenting with blockchain sharding, and then its advanced new version, BlockEmulator-X. The first part covers what BlockEmulator is, how it grew, its community, architecture, and the broker chain protocol. The second part focuses on BlockEmulator-X, what was rewritten, why, and how it works. Here's the plan. This tutorial has two parts. Part 1 introduces BlockEmulator, the open-source sharding platform, what it is and why, its timeline and community, the 5-layer architecture, and the broker chain cross-shard protocol. Part 2, the main focus, is BlockEmulator-X, the advanced version 2.0, the rewrite, what's new, its architecture, a safer execution model, and a live demo. Blockchain sharding is the leading path to scalability. It splits the network into parallel shards. But the bottleneck is evaluation. A real test network is expensive and not reproducible. A pure simulator skips real consensus, networking, and storage, so its conclusions don't transfer. BlockEmulator closes this gap, a controllable, reproducible testbed that runs real blockchain logic. BlockEmulator is an open-source blockchain testbed purpose-built for sharding research. It implements a complete but lightweight blockchain, so a researcher only implements their own new protocol. It gives you the real blockchain stack, ships built-in sharding mechanisms, replays real Ethereum transactions, is fully configurable, measures performance automatically into CSV logs, and runs on Windows, Linux, and Mac OS. BlockEmulator's story is best told through its publications. In 2022, the broker chain paper introduced the foundational cross-shard protocol. In 2023, the team released the BlockEmulator technical paper, the platform's official handbook, on AR14. In 2024, a full open-source user manual followed. In 2025, the platform was formally published in IEEE Transactions on Services Computing. And in 2026 came BlockEmulator-X, the advanced version, with a 217-page guide. BlockEmulator is far more than code, and the proof is real. The map on the left shows its user base spread across many countries and regions, with thousands of users worldwide. The screenshot on the right is the live open-source repository on GitHub, with its stars, forks, and a steady commit history. On top of that, BlockEmulator has been adopted in 10 peer-reviewed papers at venues like Infocom, IEEE/ACM Transactions on Networking, SRDS, and the Web Conference. It is documented with English and Chinese handbooks and a 217-page guide, and it won a prize at the IEEE ICMC 2024 contest. BlockEmulator uses a 5-layer architecture. Each layer handles independent functions and talks mainly to its neighbors. The storage layer keeps persistent data on BoltDB. The data layer defines accounts, transactions, blocks, and the state tree. The network layer handles peer-to-peer communication and bandwidth control. The consensus layer runs intra-shard consensus, PoW or PBFT, and inter-shard consensus through broker and relay. And the utilization layer orchestrates the whole experiment. This layering lets a researcher swap in their own protocol without touching the rest. One protocol deserves a closer look: broker chain. The challenge of account-based sharding is that when the sender and receiver live in different shards, a single transaction must touch 2 shards at once, and atomicity is expensive. Broker chain, from Infocom 2022, solves this with a broker account that exists in both shards. It splits one cross-shard transaction into 2 intra-shard ones. Atomicity is preserved without heavy cross-shard consensus. BlockEmulator ships it built-in, alongside Relay and CLPA. That covers BlockEmulator, the platform. Now to the main focus of this tutorial, Part 2, BlockEmulator-X, the advanced, rewritten version of the platform, also known as version 2.0. BlockEmulator-X is a ground-up rewrite of the platform, version 2.0. The team rewrote it for three reasons: to provide more standardized code, to make user-side secondary development more efficient, and to reduce potential bugs. The original version is now called version 1.0. The rewrite began in late 2025, and its major contributor is Mr. Huang. The same mission as before, a sharding testbed, but on a much cleaner foundation. BlockEmulator-X brings 6 main upgrades over version 1.0. First, configuration moves to annotated YAML, replacing commentless JSON. Second, storage splits the account state into 2 Merkle-Patricia tries, one for account state, one for account location, and reuses getStateDB for full EVM compatibility. Third, blocks now come in 2 types: transaction blocks and migration blocks. Fourth, networking is refactored onto gRPC. You address nodes by ID with message buffering. Fifth, execution uses a single goroutine over a message buffer, eliminating data races. And sixth, logging uses Go's standard structured logging library. BlockEmulator-X divides nodes into 2 roles. The supervisor sends transactions, acts as the committee, and collects and aggregates system metrics. There is exactly 1 supervisor per experiment. The consensus nodes, called workers in version 1.0, handle block production and consensus. Within a shard, they run inter-shard consensus. Across shards, they run cross-shard consensus for transaction relay or account migration. The figure shows the example 4 by 4 plus 1 deployment for shards, for nodes each, plus 1 supervisor. One upgrade is worth a closer look: the execution model. In version 1.0, every time a node received a message, it spawned a brand new goroutine to handle it. If the timing wasn't right, that goroutine would sleep and wait. With many messages, this risked data races and wasted threads. In version 2.0, incoming messages simply land in a buffer, and a single goroutine pops and processes them in order. Messages are handled in a strictly serialized way. No data races, no concurrency surprises. It's a smaller, safer, more predictable design. Finally, let's see BlockEmulator-X actually run. The repository ships a built-in experiment. A single command, bash example_run.sh, launches a default system of 4 shards, 4 nodes per shard, and 1 supervisor. It even downloads dependencies and compiles the code for you. In the demo that follows, you'll see the nodes launching, transactions being injected, blocks reaching consensus, and performance metrics being written to CSV logs. Let's watch BlockEmulator-X in action. Next, we will walk through the runtime demo for BlockEmulator. First, clone BlockEmulator to your local machine. Here, I have already cloned the repository in advance. Open the project with Goland or with another IDE that you prefer. First, let's look at the BlockEmulator directory structure and introduce the main folders. The CMD folder contains the program entry points, including commands for starting consensus nodes, the supervisor, network loading, and transaction file generation. The config folder contains configuration loading and parsing logic, corresponding to files such as config.yaml and ip_table.json in the root directory. The consensus folder implements the consensus protocols. The core module is currently PBFT, including PBFT node logic, intra-shard and cross-shard operations, and migration mechanisms. The package folder is the common foundation library for the project. It includes blockchain data structures, transaction execution, networking, message definitions, storage, logging, shard partitioning, broker, VM, and other shared capabilities. The supervisor folder contains the supervisor node logic. It is responsible for transaction injection, committee and shard scheduling, and the collection and aggregation of experiment metrics. Now we open config.yaml and focus on the parameters used by this experiment. Here, the configuration defines the shard number, node number, block size, and other runtime options. For this run, the shard number is set to 4, and each shard contains 4 nodes. The transaction source is set to random, and the experiment will generate 500,000 transactions. After checking the configuration, run the script to start the experiment. Make sure the script uses the same shard and node settings. Now we can see that the experiment is running. The experiment has finished. We can inspect the generated results under the EXP package. The block_record folder records block-related experiment data. The logs folder records the log output from each node during the experiment. If anything goes wrong, researchers can use these logs to identify the cause. The results folder records performance metrics such as TPS and latency. Next, we will demonstrate the smart contract testing workflow. First, write a user-defined smart contract. Next, write a custom scenario file that will be used to generate the trace file. For the exact format, you can refer to the example.txt file. Now run the trace file generator. We can see that the trace file has been generated successfully. Next, modify the configuration file by copying the generated trace file path into the configuration. After the configuration is updated, run the script to start the experiment. The experiment has now started successfully. After the experiment finishes, the smart contract-related experiment data should be checked in the log files. In the log output, we can see the deployed smart contract address, as well as the results produced by calling the smart contract. That concludes the full block emulator demonstration. Thank you, everyone.